Hello guys, welcome back to another video on my channel. So in the last video we talked about linear combinations and spans as both a noun and a verb. So I urge you to look at that video before this one because this is actually a linear algebra lecture series. With that being said, let's get started. So far, as I said, we've explored the concept of linear combinations and spans via the the idea of lists of vectors. And when I say lists, it means a finite number of vectors. In this video, we will actually explore linear independence and, of course, prove some results based on that. So let's define that first. A list of vectors v1 through vm, which are vectors in the vector space V, is called linearly independent if the only choice of a1 through am, where all of them are scalars in the field, that makes the following true, which is the equation a1 v1 plus dot 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 plus am vm equals 0, is if a1 equals a2 so on equals am is identically 0. So what that means is a list of vectors is called linearly independent if the only way to write 0 as a linear combination of the vectors in that list is if each of those combination coefficients or scalars is 0. And as with span, the empty list is defined to be linearly independent, just like the span of an empty list was just the trivial 0 element. The empty list is defined to be linearly independent. So what this definition here also means, and you can prove that very easily, is that v1 through vm is linearly independent if and only if each element of the span of v1 through vm has one representation as a linear combination of v1 through vm. So if there exists coefficients a1 through am for such that some v in the vector space can be written as a linear combination using those coefficients, those are the only coefficients. There's no other coefficients if that list is linearly independent. This is easy to prove. This is how you proceed to prove this, like you prove any kind of uniqueness result. You assume a different kind of representation exists, subtract them, and you then use this definition that to write 0 as a linear combination, the coefficients have to all be 0 for if the list is linearly independent. Take an example now. So suppose a1, a2, a3 belong to the field and the vector space we're taking is f4. Then if we take the vectors 1 0 0 0 0 1 0 0 and 0 0 1 0, if you try to write 0 vector of f4 as a linear combination of these three using some scalars a1 a2 a3, then the only way to do this, and you can do this by evaluating each component of these vectors, is if a1 equals a2 equals a3 equals 0. So that means this list of three vectors is linearly independent in f4. And I guess a more trivial example is a list of length 1, which means it has only one vector in a vector space, is linearly independent if and only if the vector in the list is not 0. Because if that vector in the list is 0, then it's not linearly independent, because you can express the 0 element in many different ways. In terms of the 0 of the list, you can multiply by any field the 0 vector of the list and get 0. So there's many ways of expressing the 0. So if the vector in the list is non-zero, then the list is linearly independent. Now let's define linear dependence. We have linear independence. Let's define the opposite. A list of vectors in V is called linearly dependent if it is not linearly independent. More precisely, a list of vectors in V, V1 through Vm, is linearly dependent if there exists A1 through Am, which are all elements of the field, not all zero. So there must be at least one non-zero Am, Ai in them, such that A1 V1 plus dot 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 Am Vm equals 0. This is, if you see, the logical negation of the definition of linear independence. For then there we had for all that all a1 through am equals 0. Now there exists a1 that which are not all 0. So that is the logical negation. An example of this is the list 2 3 1 1 minus 1 2 7 3 8 is linearly dependent in F3 because we have coefficients 2, 3 and -1, such that when you take a linear combination of these three vectors with those coefficients, you can write the zero vector. So there is a non-trivial way of writing the zero vector, and therefore they must be linearly dependent. And every list of vectors in V containing, and that is a typo, I'm afraid, containing the zero vector is linearly dependent, because you can write the zero vector of your vector space by setting all the other coefficients to 0, but the coefficient of the zero vector in the list to 1, and that is a non-trivial way of writing the zero vector as a linear combination. Let us now prove a lemma that will turn out to be quite useful to us. Suppose V1 through Vm is a linearly dependent list in V. Then there exists some index k which belongs to the set of indices 1 through m, such that vk belongs to the span of the k minus 1 vectors before it in the list, which is v1 through vk minus 1. Furthermore, if k satisfies the condition above and the kth vector is removed from the list v1 through vm, then the span of the remaining list after removing the vk is the same as the initial span. So span is unaffected because it equals the span of v1 through vm. Span of v1 through vm with vk removed is equal to the span of v1 through vm. That's what this the second part of this statement is saying. So you remove the vector that is a linear combination or linearly dependent on the k minus 1 vectors before it from your list, and the span of that list with the vector removed equals the original span. That's what this part says. Let's prove it. Let's prove the first part, that vk belongs to the span. So because the list v1 comma vn is linearly dependent, that was given to us, there exist scalars a1 am belong to f, not all 0, such that a1 v1 plus dot 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 am vm equals 0. This is just the definition of linearly dependent. Now let us choose k to be the largest element of the index set 1 through m, such that the coefficient for the k, ak, is non-zero. And since ak is non-zero, then you can write vk from this equation here, this decomposition here, as minus a1 over k v1 minus dot 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 minus ak minus 1 over ak vk minus 1. We can divide by ak because ak was non-zero by how we chose the k. So that means vk is a linear combination of v1 through vk minus 1, right? Because this a1 over ak is just a coefficient. So this is a linear combination of the k minus 1 vectors before it. meaning that vk is in the span of v1 through vk minus 1. That's it. That's the first part proved. Now let's prove the other part. So now suppose k is any element of the index set 1 through m such that vk belongs to the span of v1 through vk minus 1. Let b1 dot 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 bk minus 1 be scalars such that vk equals b1 v1 plus dot 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 bk minus 1 vk minus 1. Call that equation 1, and this is because we suppose vk is in the span. The definition of this being in the span is you can write vk as a linear combination of v1 through vk minus 1. Suppose u is in the span of the original list, which is v1 through vm. Then there exists coefficients c1 through cm in the field such that u can be written as a linear combination. That is the definition of being in the span, that u can be expressed as a linear combination of v1 through vm. So you have u decomposed as c1 v1 plus dot 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 cm vm. Now in the above equation for the decomposition of u, replace the vk because vk is included in this v1 through vm list. So in this linear combination, there is a ck vk term. Replace that vk with the right hand side of equation 1. So write vk using substitute for vk using this b1 v1 bk minus 1 vk minus, which is the right hand side of 1, such that then that there is no vk dependence in the decomposition of u. So that means that u is a linear combination of the list v1 through vm, but with vk removed because vk has been substituted. So u therefore belongs to the span of v1 vk minus 1 vk plus 1 vk vm. So notice this is the list with vk removed. So u belongs to the span of v1 through vm of the original list, and u also belongs to the span of the list with vk removed. And removing the kth vector from v1 through vm does not change the span of the list, and this is what we had to prove. That's it. So this was a simple argument relatively. We just chose k in a way that gave us the form that we wanted, and yeah, we also proved that removing that linearly dependent element does not change the span. Notice the ordering of this lemma, that the vk, this lemma guarantees that a vk is in the span of the vectors before it. So this means the ordering is important, that the third vector belongs to, in this case, the span of the first and the second one, for example. It's not depending on the vectors after. Just because, of course, we could re-evaluate, reformulate this as vk belonging to the span of the vectors that come after it. But in this version, we're using the vectors vk depending on the vectors that come before it. And just remember this this placement is important. This will be a notable point in the next result. And also a point I would like to make is this proof. This proof is good for the non-trivial cases. If you take the trivial case where k equals 1, then you can no longer use this proof, although it's a very trivial statement to prove for the k equals 1, the unit list length case. But that's just a small point. I won't be proving that case. It's a simple case. Maybe you can do it, or maybe just intuit, but you won't be able to really use this proof. Won't work for that. You'll have to use a more simpler argument just for that case. And of course the empty list is kind of a vacuous case. Okay, here comes the theorem. which is actually quite important. So in a finite dimensional vector space, the length of every linearly independent list, of vectors is less than or equal to the length of every spanning list of vectors. So there is an inequality on the relative lengths of linearly independent lists with respect to spanning lists on a vector on a finite dimensional vector space, which is what we'll be working for, as I said before. Suppose u1 through is a linearly independent list in V. Suppose also that w1 through wn spans V. Notice m and n are different because we have to prove that m is less than or equal to n, that the size of the linearly independent list is less than or equal to the size of the spanning list. We will be using induction. We'll be doing this inductively through a process which involves a bunch of steps, where we'll be adding one of the u's each time while removing one of the w's at each step. So let's start. Step 1, add u1 to the list w1 through wn, which is the spanning list, which spans V, of course, by definition. So you add it again, and this is where the position matters. You add it to the start. So u1, w1 through wn. Now this list is linearly dependent because remember how w1 through wn is a spanning list and u1 is just an element of V. So u1 naturally belongs to the span of w1 through wn. Therefore, one of the vectors is in the span of the others, or can be expressed as a linear combination of the others. Therefore, this list is linearly dependent. Then by the lemma before that we proved just before this, one of the vectors in u1, w1 through wn can be expressed as the linear combination of the vectors before it. Now, this is where the placement is important. There's nothing before u1, so we can't. So u1 is not the vector, is not a vector that can be written as a linear combination of the ones before, because there's nothing before u1. However, any of the w's can be chosen, says that it is a linear combination of the ones before. So choose that w. And the lemma from before also guarantees that if you remove such a w from this list, which was a linear combination of the vectors before it, which in this case would also include a u, because u is at the start position, removing such a w will not change the span of the original list, which is u1, w1 through wn. So the new list of size n, after removing that w, because we added a u and removed a w, so the size does not change. The new list of size n consists of u1 and the remaining w's, and of course by the lemma still spans V. So we've removed a w, added a u, kept the list size the same, and also ensured that it still spans V, so that it is still a spanning list. Now, step K, where K equals 2 through M. Assume that the list of length n from the previous step to K, which is step K minus 1, spans V. Then add the kth vector, uk, to this list right after u1 through uk minus 1. So add it to the right of uk minus 1, but to the left of all the w's. The w's are on the very right. Note that if you have such a list of length n from step K minus 1, we were adding u's at the starting position, or to the left of the w's. We would have by step k minus 1 u vectors. So all I'm saying is add a kth one right after uk minus 1, but still to the left of all the w's. Since this is linearly dependent, because this k minus 1 list that you have is still a spanning list, so the uk belongs to the span of the k minus step k minus 1 list. So this is a linearly dependent list. Use the previous lemma again to see that one of the vectors in this list is in the span of the vectors before it. That's what the lemma said. Now notice that that vector, which is a span of the which is in the span of the vectors before it, cannot be among the u1 through uk, because u1 through uk are linearly independent by this beginning that we assume that the u's are linearly independent among themselves. So this vector cannot be among them, which was a span of the ones before. It has to be there. That means that there must be at least one w, because if there isn't a w, then this list is not linearly dependent. It is linearly independent, which violates what we said here, that this is linearly dependent because UK was in the span. This was the spanning list. So that means in order to not violate that, we must have at least one W. Without W's, we'll violate the linear dependence and the spanning property that we assumed, which was also known as the inductive hypothesis. So that means at least one W exists, and that W, by this lemma, depends on the vectors before it. So we can remove that while not changing the span, while ensuring that the new list with that W removed, with the KU ones, is still a spanning list in V. Fair enough. We do that for k equals to m, this step. So after step m, we have added all the u's, because that was the size of the list of u's. And we terminate the process because we run out of u's. There's nothing more to add. Note that at each step we added a u in the current list, or the list that we obtained from the previous step. The lemma from before implied the existence of some w that we could remove at any given step. Otherwise, we would violate linear dependence and spanning property, as discussed before. And that means there must always exist, whenever we add a u, there must always exist some w that we remove. So that means we cannot run out of w's before the process terminates, or before we run out of u's, which is, the process terminates when we run out of u's. So we cannot run out of w's before we run out of u's, also known as process terminating. Because if we run out of w's, then we violate the linear dependence by adding a new vector and the spanning property. So that means that m is less than or equal to n, where m is the size of the linearly independent list and n is the size of the spanning list. Which means we can have more w's. We can have more w's than the u's, but not the other way around. Because if we have less w's, we run into inconsistencies, especially with respect to that lemma that we had before. Okay, that is a proof. Let me know if you have any questions. This, I guess, might have been a little new to people who don't know about induction or this kind of arguments. But yeah, feel free to pause the video at any time, as I said at the beginning of this series. I don't expect you to pick it up from the get-go. Example: no list of length 3, no lists of length 3 span R4. And this again is because of this inequality. The list 1 0 0 0, 0 1 0 0, and 0 0 1 0 and 0 0 0 1. So a list of 4 elements has length 4 and is linearly independent in R4 as we determined earlier. So this list of 3 elements, length 3, 1 2 3 minus 5 4 5 8 3 9 6 7 minus 1 with length 3 does not span R4 because of just violating this inequality. So that is a very neat property. A kind of, you can think of this example as a corollary actually. Going on to our next important result now, that every subspace of a finite dimensional vector space is finite dimensional. By intuition, it makes sense. If your parent vector space is finite, anything, a subset of it, must also be finite. Sure, but let's make that a little rigorous. Suppose V is a finite dimensional vector space and U is a subspace of V as given. Step 1. If U is the trivial subspace, which is just the 0 element, then U is finite dimensional because it just has one element. Or you can just span it with, the 0 vector or list of size 1. And we are done. That's it. That's the trivial case. But if U is the non-trivial subspace, so U is not equal to the subspace 0, then choose any non-zero vector U1 in capital U. And we can always do that because U is a non-zero subspace. So there must also be a non-zero vector, at least one non-zero vector. So choose that. And add step K, where K goes from 2 to whatever the dimension of your thing of your process is. But let's just say step K. We don't know what the bound is. Assume that U1 comma uk minus 1 is a linearly independent list from step k minus 1. Fair enough. Then if U equals span of U1 through uk minus 1, if U is spanned by that k minus 1 linearly independent list, then U is finite dimensional and we're done, right? Because k is finite. So list of finite size spanning U means U is finite dimensional. That's it. But if U is not spanned by the k vectors, U1 through uk minus 1, so k minus 1 vectors, I mean, then choose another uk belongs to U such that uk is not in the span of U1 through uk minus 1. What this then does is U1 through uk minus 1 is already linearly independent by the inductive hypothesis when we said assume. We're choosing a uk that's not a linear combination of those, or which is not in the span of those k minus 1 vectors. So that means U1 through uk, now when you add uk to that old list, will be a linearly independent list again. So that means after each step, we construct a linearly independent list. This linearly independent list, being a linearly independent list, cannot exceed any spanning list of V by the previous theorem. Because remember, we have this bound from the previous result: linearly independent list less than or equal to spanning list. So a linearly independent list in U, which is a subspace of V, is also a linearly independent list in V. This is a very trivial thing. You don't really need to prove that because it's very easy to see. Any linearly independent list in U is also linearly independent in V because the linear combination is inherited as we go from vector space to subspace. Therefore, this process of us adding UKs that are not in the span of the the list from the previous step, this process of adding must end. So we can't add infinitely many times to infinity. We are bounded by the size of the spanning list of V, which is also known as the dimension of V. Then by the so that's that was the result of the previous theorem. Therefore, this process must terminate. You cannot keep adding new vectors which are not in the span and keep enlarging your linearly independent list. So there must come an exit condition or termination condition, which is this: if u equals span of u1 through u, or span of the list that you have at that step, then u is finite dimensional and we're done. That's the exit condition that we get because this process must be forced to terminate. So that's it. So therefore, this process terminates. Whatever list you construct which is linearly independent should have a finite number of elements because of the upper bound of the theorem. And U is finite dimensional. That's it. That's all there was to prove and do in this video. So please like, share, and subscribe to my channel, guys. Spread the word of gamma di gamma. And in the meantime, peace out.